Hi friends, hope you are doing well. I am Dr. Ganguly. Welcome to my channel. So today I will be discussing a concept known as the digital twin, and essentially this concept has become very important in recent years. It's something which encompasses modeling, simulation, data science, machine learning, prognostics, diagnostics, predictive modeling, and many other fields. So recently we wrote a book on digital twin, that's Digital Twin, a Dynamic System and Computing Perspective, and I'm going to discuss some of the elements which are discussed in the book, and I'm going to provide a preview to you about this book, and in the comments I'm going to also give you a link to this book. So this is certainly going to help any students in engineering, science, systems, as the case may be, because we can think of a digital twin not only of engineering systems such as a car, aircraft, factory, city, ship, or even the whole planet, but we can even think of digital twins of the human body, so that would be a medical application. We can think of digital twins of the ecosystem, so that would be an application in the environmental sciences, and we can use digital twins in various fields such as in agriculture, in shipping, even in strategic thinking and business. So let's begin. So essentially a digital twin is a computer model of the physical system. Now, as you all know, if you recall your physics courses in high school, we have been modeling physical systems for a very long time, ever since Newton and his fellow scientists started the whole process of modeling. So essentially modeling means that you take a certain physical system and you write certain equations governing this physical system, and then you solve these equations. Now, how do you write these equations? Essentially, you use the laws of physics to write these equations. Sometimes you may use the laws of chemistry also, and so on. So essentially these mathematical models of physical systems have been the cornerstone of engineering and science for a very long time. So what has changed in the digital twin? So what really changed is the fact that nowadays many systems have a lot of sensors in them, and these sensors are not only sensors such as temperature, pressure, vibration sensors, but may even be data coming from cameras, from sound recording systems, and so on. So essentially there is a very large amount of data present there from all kinds of systems, and this has happened because of the explosion in the field known as the Internet of Things. So nowadays internet connectivity is not only there in devices such as phones and laptops and iPads, but also in things such as washing machines, refrigerators, cars, and so on. So you can have situations where your washing machine could start at 3 a.m. in the night when the load is least or the cost of power is least. So all these kind of things can be done with the Internet of Things. So essentially what this data has done is that it allows you to improve your physical model, and in some cases you can create what is known as a data-driven model from the data which you have obtained. So essentially in data science, one of the things you often do is you try to do a regression curve fit to a set of data. So essentially a regression model is a very basic model of a system which is obtained totally from data. So it can be considered to be an empirical model of the system. Now, physicists would like to actually create a model of the system from the understanding of the physics of the problem, and that is often the case. For example, if you think about the things you studied in your class 12, such as the motion of a pendulum, we essentially try to resolve the forces which act on this pendulum, such as the force due to gravity and the weight and so on, and the tension in the string, and then we come up with the governing equation of motion for the pendulum, which we think will essentially let us describe the motion of the pendulum. Now, if you remember this problem, the problem essentially involves sine theta, and then you make an approximation that sine theta is approximately equal to theta for small angles, and then you are able to solve this as a linear system. So this is the process which is often done in engineering and science, is that a model of the system is devised. Sometimes simplifications are made which allow the model to become amenable to an exact or closed form solution. Now, as far as engineering is concerned, because many of the systems are not simple uniform systems, what we often do is we do numerical methods. So essentially, you must have heard of various numerical and computational methods for different systems, and all these are coming because the mathematical model is not something which can be solved in closed form through partial differential equations and so on. So now, what do we do now? Essentially, we can create math-based models, we can create physics-based models, we can create data-based models. So all these are legitimate, and the model you choose, of course, depends on the system you are dealing with. So one of the things you often do in a digital twin is that you start off with a physics-based model. So this model may be a very simple model of the system, and we will call this the baseline model of the system. Now, as the system evolves in time, you update this model using data, and essentially you can think of a system such as a car which is purchased by a customer, and then different customers subject it to different load cycles and different paths and different levels of performance and so on. So each car is essentially evolving separately, but we can track each car by its VIN number, for example, and therefore what we can do is we can construct a digital twin for each car. So instead of just having a physics-based mathematical model of the particular car you are thinking of, you essentially now have thousands, if not millions, of digital twins which are specific to a particular car concern. If you are thinking of an aircraft, each aircraft can be defined by a tail number. So essentially you could have a digital twin for each tail number, and this allows certain things to take place. This allows some engineer or data scientist sitting somewhere to access all this data from the cloud and then perform all kind of number crunching, visualization, machine learning to figure out if there is any problem in that particular system. So maybe that system needs maintenance, maybe that system is getting close to failure. So whether it is a car, whether it is a gas turbine engine, wind turbine, or a human being, we can essentially construct a digital twin and we can monitor the health, performance, and remaining life of this system. So this is essentially one of the long-term goals of digital twin. Now, in another case, suppose you had a digital twin of a city or for the planet Earth, you could essentially use this digital twin to create simulations and to see as to what changes could be made in the system to help to improve performance. For example, if there is a city and the city is producing a certain level of carbon, then what can be done is the traffic could be changed. Maybe all the washing machines could work at a different time. Maybe you could set up the timing of all devices such that they match the production of renewable power such as wind and solar. So when the sun is shining bright, the machines are running more. Then when the wind is strong, the machines are running to a greater extent. So you can get the hang of this whole thing, that the digital twin essentially creates a tailor-made and optimized system. So that is the final goal. And so if you could accomplish this goal, you could save millions, if not billions of dollars, and maybe even trillions of dollars of money. So of course, this concept is not completely new. I would say the concept of updating the math model or the physics model has been going on since the time Kalman filters started up. So essentially, estimation theory is something which started this complete process off. So if you are an electrical engineer by training, you already know that the Kalman filter essentially takes measurements and then tries to actually give predictions from the model. But of course, the Kalman filter would like to have a reasonable baseline model to start with, and also it requires certain estimates of measurement uncertainty and system uncertainty. Uncertainty and noise are big things in digital twin, because the uncertainty is coming from the noise in the sensors, which can be Gaussian noise or non-Gaussian noise. So Gaussian noise is basically the kind of random noise which you see, sometimes also known as white noise. Non-Gaussian noise can include, for example, outliers which are not following any normal distribution. So again, all these things are possible, and so one of the things to improve the performance of digital twin would be to remove any outliers or bad data before you try to do the digital twinning, as the case may be. The other thing which is the source of uncertainty is the deficiencies in the model themselves, and this of course is a vast subject in its own right. The subject of uncertainty quantification is often used to quantify uncertainty in modeling. So uncertainty in modeling can come again from random uncertainty, or it can come from bias inherent in the model. So all these are things which need to be accounted for. Now, because sometimes the physics-based model take a lot of time to run, one of the things you can do is set up surrogate models, and one of the best surrogate models for digital twin is the Gaussian process model, and that we discuss in the book in some detail. So Gaussian process is a type of Kriging, so it's related to machine learning, so that's where machine learning comes in. Now if you want, you can also set up neural network based models which are surrogate models for any system. So of course there is always the issue of model complexity. So how complex should your model be? So in general, from the theory of parsimony, you should use the simplest model possible. So I think I have made a short on parsimony, and that is basically the theory that you should always use the simplest model possible. And often you see in data science that regression works out very well, because in many cases a simple linear approximation is a pretty good model. But if you feel you need to enhance model complexity, for example, if you are dealing with a dynamic system, you can go for multi-degree of freedom systems. You can also include nonlinearity in the system, because many physical systems and real world systems are actually nonlinear, and these are subjects we cover in our book. Finally, there are many companies which have brought out specific tools for digital twin. So there is the Microsoft digital twin. For Azure, that is Tensorflow, which can be used for digital twinning. Amazon and other companies have also brought out products, including Siemens. So essentially in all these company type of digital twins, the digital twin is largely constructed using data, and this is the situation in most real systems as of today. If you do not have a model, you can still construct a digital twin largely from data. So if you are dealing with very complex systems such as smart cities and so on, it's very hard to construct a physics-based model for such a system. So you may completely rely on data. But if you are relying on an engineering system such as an aircraft or a gas turbine or a car, you may actually have a decent baseline model of this system developed by engineers and scientists over many years. You could use this model in a differential equation form, you could use it in a state space form, and then essentially you can update this model yourself. So a lot of this kind of work is going on in different companies, but because a lot of this information is proprietary to companies, it often does not come out in publication. So that's something to keep in mind, that model-based digital twin is happening in many situations in the real world. So this was my short introduction to digital twin, and like I again mentioned, this is the book. I hope you can see it on your video here, and this book is written by several of us who are professors or scientists in industry and consultants, and it will certainly help you improve your knowledge of digital twin. If you want to read this book, you need some knowledge of differential equations, you need some knowledge of matrix theory. So these will generally be enough for you to read this book. Maybe a little bit of calculus thrown here and there, but calculus should be something you already know if you know differential equations. So that was my take on the digital twin concept, and I will see you in a video sometime soon. See you soon.